All right, what we're gonna do, we've talked about lenses and mirrors. The new problem set will be coming out this afternoon, maybe. With lenses and mirrors, in both situations, objects are on the left and their object distance is always greater than 0. But with lenses, if the object is on the right, the object distance is negative. For focal length, if the focal length is greater than 0, the focal point is to the right of the lens. If the focal point is greater than 0, the focal point is to the left. If the focal length is negative on a lens, it's to the left. If the focal length is negative, it is to the right. If the image is to the left of the lens, the image distance is negative. The image distance is positive if the image is to the right. Let me get that blown up. If on a mirror the image is to the left, it is greater than 0. If an image is to the right, it is less than 0. Images to the left of lenses and right of mirrors are virtual. Images to the right of lenses but left of mirrors are real. For both lenses and mirrors, this equation holds true for both. That 1 over the focal length is equal to 1 over the image distance plus 1 over the object. Everything, lenses and mirrors, how those numbers are applied are based on the situation. For magnification, M is equal to negative I over O. The magnification, if its absolute value is greater than 1, it has been enlarged. If that absolute value is less than 1, it has been reduced. If the magnification is greater than 0, it is upright. If the magnification is less than 0, it has been inverted. Enlarged, reduced, upright, inverted. So if I gave you a magnification of -4, this information that you get from that is that the image has been inverted and it has been enlarged. So this would become like that. So we could sit here, what's going to happen on the test is that one of the problems you will be either, there are 3 versions. There will be one of the problems you'll either get a mirror or a lens. The mirror or lens will be concave or convex. The object will be in front of or behind the focal point. And then you guys can just have at it. Hold on. Ah! I'm dying. It's all the trees. So what we're going to do is just a rapid fire problem. In fact, we'll do it this way. We're going to go old school on this. All right. Odds or mirror, evens or lenses. All right. We got a mirror. Odds are concave, evens are convex. Concave. I want, oh, we could do it this way. We did concave. Okay, fine. What would you like to request?
Probably a lens.
Lens, concave or we'll do a concave lens. All right, that's great. I thought we were going to let the dice decide, but students do have a choice. Now, for this concave lens, let's just discuss it. Which one looks like a concave lens? The one on the left or the one on the right? The one on the right. Does the focal length for a concave lens, is it positive or negative? All this stuff you're going to have to know for the test. It's going to be negative. Concave lenses, are they diverging or converging lenses? They're diverging. The thing that I remember is for a fact that that convex lens is a converging lens. I mean, it's obviously the lens, as a kid growing up, that's the lens that you use to burn ants, because it's a magnifying glass. And so the lens of the convex lens converges the light to a point. So we have a concave lens. Trying to think of the math. It is a concave lens, comma 6. So if it's a concave lens, comma 6, sometimes I put the unit in, sometimes I don't. I've talked to optometrists. They say that's fine. But the 6 is in what? Diopters. A diopter is what in common units? Inverted meters. So the focal length, we'll call that D. Since it's a concave lens, our logic says that the focal length must be negative. Put the diopter in, negative 1/6 meter. And so that becomes 16.7 centimeters. I think that's what it is. Yeah. So negative 16.7 centimeters. Now, it doesn't really matter if the focal length is before or after, because we're still going to get with a negative answer. Richard, what do you want as your object distance? 7? All right. So object is 7. First thing I want to do is I want to calculate the image distance. So 1 over F is equal to 1 over O plus 1 over I. 1 over F minus 1 over I is the O. O is equal to 1 over I. So I is 1 over F minus 1 over O inverted. And so those are the distances. And that is not a 0 because I know the differences between when a 0 is in the denominator and when it's an O. So this becomes 1 over negative 16.7 minus 1 over 7 inverted. Let's do this. 16.7 inverted minus second answer minus 7 inverted. So we have a image distance of negative 4.9 centimeters. So you've kind of chosen a weird object distance because the image is going to be so close to it. Oh. Magnification. Negative I over O. Negative 4.9 over 7. So positive 0.7. Now what that tells me is I know what this image looks like. Yes, I brought my ruler. Yay. All right. Yes.
On the test, I know we can bring in rulers and protractors, and I know that you draw to scale with your grader and your ruler. Do you want us drawing everything exactly to scale?
It has to be to scale, otherwise we really won't do that.
Okay.
Now I don't care about specific distances, like the object has to be 3 centimeters long.
Okay.
All I want is for it to fit on the page.
Okay.
Looking over at past tests, try to be somewhat faithful to the ratio of magnification. There's some people who just don't care, and then they drew, instead of lines, they draw these huge arcs.
Right.
And it looks obvious that I can tell, or it's obvious I can tell. Who knows what they're doing?
Okay, but in general,
You have to do a seriously. The magnification must be in the proper ratio of the whole thing, otherwise the whole thing's just going to fall apart. And it's not because I want it to be, like, I'm not demanding it. I'm just saying, if you want it to work out right, you got to do it. Now, because the image distance is negative, am I dealing with a real or virtual image? What? Richard just shouted out a word, and it's virtual. If the image distance is negative, it is always virtual. Because it's a virtual image, is it to the left or right of the lens? It's to the left. Once again, wrong. Because the magnification is positive, is the image upright or has been inverted? It is upright. It's positive. Has it been enlarged or reduced? It's been reduced. Magnitude of magnification is less than 1. All right. So I have all the information that I need, and hopefully you've written this down because I'm about to go into drawing mode. The lens is concave, focal point is to the left, object is to the left, image is to the left, so I can kind of write this so that the lens is kind of off on the right-hand side. You want to draw your optical axis first. your ray plane or the lens plane next. Focal length is negative 16.7. That's the biggest number we have. So I'm gonna do 4, 8, 12, 16. I've got a big block as 4. So 4, 8, 12, 16.7 means that the focal point is there. Now obviously there is a focal point over here, and what I'm going to do, I'm just going to kind of keep that in mind. Object is 7. The image is 4.9. Now the magnification is 0.7. So I'm going to draw my object two big blocks. So let's say, so that is 4 big blocks. So 4 big blocks times 0.7 is 2.8 big blocks. So that makes it about that. So that's the first thing that I want to do. And let me actually, I'm going to extend this ray diagram a little bit further. Now, when you do this on problem sets, we kind of expect a little bit of precision, coherence, stuff like that. On a test, we understand that this is a combat situation. We only want 2 rays in a testing situation, but for 3 on a problem set. When you're doing this, we're not expecting perfection. We are expecting some sense of, you know what you're talking about. Ray 1, the easy ray, the ray that just, it's obvious, is the ray that goes directly through the middle of the lens. Rays that go through the middle of the lens are unaffected by anything. And so they go like that. The second easy ray is the third ray, or I'm sorry, not the third ray, parallel ray. Now, because it is a concave lens, concave lenses diverge, which means that the light gets bent away so the rays intersect at that point. And that would be good enough on a test. The third ray, the tricky ray, if you aim a ray at that focal point, or the anti-focal point, for this situation, in the optics PDF that I sent you, there's something like this in there. The ray becomes parallel. And in fact, what I'm going to do is I'm going to go and the ray gets traced back. And so all three rays are focused at the same point. And so that is this situation. There's all sorts of permutations. In fact, there would be two rays in lenses, concave, convex is 4, in front of, behind, focal point is 2 more, so that's 8. Say again? On the problem sets, I want you guys to work the third ray. On the test, you don't have to draw it. Okay.
How do you know if the line needs to be dotted?
How to be what?
If it needs to be dotted or if it needs to be
All right. I'll deal with your question first. When you've got this, this is one of the reasons why I'm not going to hold anybody really accountable for the third ray on the test. Oh, wow, I got it right. In situations where the object is behind the focal point, here, we would be playing, the object and the focal point would be the ones lining up. Because the object is between the focal point and the lens, I aim a ray at F prime. There are the three main rays. The first ray through the middle. The second ray starts parallel and either diverges away or diverges from the focal point. In this case, this ray diverged away from the focal point, or it converges to the focal point. The third ray is a ray that you gotta kind of look at it, and it depends on the situation. In this particular case, the light, if you aim it at the inverted focal point, or F prime, the ray becomes parallel. Through the middle unaffected. Parallel gets bent. Bent ray becomes parallel. So those two last rays, parallel becomes bent, bent becomes parallel. That's how you're supposed to remember this. Now, I'm going to get to his dotted rays in just a moment, but Walisha, what's your question? It depends on the lens. In this particular case, the lens is concave, which means once the light goes through, it bends away. If you had a converging lens, the light goes through and passes through. Now your question, why do you use dotted lines and why do you use solid lines? The dotted lines are either reference lines or backtrace lines. They're the virtual rays. They're where the light isn't going. This is a virtual image. So virtual rays converge on it. Yeah. So this is, I mean, obviously this is a virtual image because it's on the same side as an object or a lens. The light, what does light do? Passes through a lens. So pass through solid, pass through solid, pass through solid. But the virtual rays will get traced back. Yeah.
So if this is a converging lens, that second ray can hit it and then go back
converging lens, first thing, that would be a depth instead of a depth draw. This ray would be unaffected.
Right.
This ray would go to the book.
Oh, okay. So it would start parallel and then go.
It would start parallel and bend towards.
Okay.
Third ray, I think the third ray in this situation, it would go, you would go from there up. Oh, I have to think about this. The third ray, that's why the third ray takes time to figure out, and by then it's really unnecessary. That's why, like, me, if I'm drawing this, bam, bam, I've got the image. I don't need to draw a third ray. I don't need to waste my time with it. So in terms of it's really, let me tell you what I'm doing. Magnification is positive 0.7 with a negative image distance. Is the image on the left-hand side? Yes. Is the image upright? Yes. Is the image reduced? Yes. So if you have positive 0.7 and you drew it upside down and enlarged and on the right-hand side, I know you don't know what you're talking about. This is just to verify that you do know what you're talking about. We use it as a double check. With your really what I'm doing is I'm looking at your magnification. I'm gonna look at your magnification number and then I'm gonna look at that image and see if they match up. All I'm hearing are mumbling and I can't see. You can make up your own height for the opposite images if you're. Now, what I would typically do as advice, when the magnification is less than 1, magnitude magnification, so you're getting a reduction, then obviously the object is going to be the bigger of the two. So I tend to draw that roughly 75-80% high on the page. In the sense that it has been enlarged, then I draw the image as the biggest thing on the page, and then divide by that and draw just so everything fits. Really only third grade looking first grade. It would be curved, but the problem with the curve is that the majority of the class are horrible artists. And so you wouldn't be able to draw. Now really, if we think about what goes on in a lens, and even I'm like, I don't want to draw this. But you asked for it. A convex lens is like this. So it's going to refract a little bit and do it twice. It's just not functional to draw it that way with a human hand. And so what I do is I just simplify it to do it like this. It's impractical, it wastes time, it just doesn't work within an R. I mean, I would then have to say, well, fine, bring your architecture drawing tools and then we'll do it that way. But no, this simple way is the best way to do it. Just draw the lens line and be done with it. Whew. In the lab today, you will have something called a compound lens. And what that is you have a convex and a concave back to back. The object is over here. And what you're going to do is you're going to figure out where the image is to determine the focal length of the concave. Now, for the most part, I think they give you the value. So all of this is just math and algebra and solving for stuff. For a compound lens, step 1, use convex only. So the first thing you're going to do is you're going to have this convex lens using a basic experiment. For the first part of the lab, you're going to have this convex lens, and for your particular lab, you're either going to open up the window and look at Martindale, or look at the door at the opposite end of the hall in Lewis. And you're going to hold up this lens on one side, and you're going to hold a sheet of paper on the other, and you're going to move the lens back and forth until you get an image of Martindale or that door on the paper. When you use this, object is infinity, so 1 over f is equal to 1 over infinity plus 1 over I. That becomes 0, so 1 over f is equal to 1 over I. So the focal length of the lens is the image distance. So you're going to hold that sheet of paper out, you're going to hold the lens, and then the distance at which it focuses, that's the focal length of your lens. Typically, it's going to be around 20 centimeters. Some of them are 18, 19, 20, 21, and 22. Same thing with the concave lenses, negative 18 through negative 22, something like that. So this part of the experiment, you're going to set up something with an object distance, and then you're going to calculate the image distance. And let's say, for the sake of argument, that f of the convex lens is 20 centimeters, and I need an object distance of 25 centimeters. So you're going to place this you're going to need a real image coming out of this lens in order for this thing to work. So the object distance, 1 over f minus 1 over o is equal to, or inverted, is I. Now notice, in a compound lens, I do not expect you to draw ray diagrams. It is, when you've got a compound lens, those ray diagrams get complex. So I don't care about it. Don't draw it. If you get one on the test, you're not gonna have to draw a ray diagram. I don't even say draw a ray diagram when you're, for that homework. So this is 1 over 20 minus 1 over 25 inverted And that's 100. I'm gonna go call an audible. I'm gonna make it 30. I want to make the numbers work right. And that's better. 60 centimeters. So the first image is 60 centimeters away from the convex lens. The magnification and start noticing that I'm putting ones on everything. Negative 60 divided by 30, or negative 2. So the magnification is negative 2, which means I'm dealing with a real image to the right of the lens. It's been enlarged and inverted. So let's just approximate where this image is going to be. If that object distance is 30, then the image distance is going to be down there. And this is I1. Place the concave lens a given distance to the right of the convex. Such that the concave lens is between the convex and I1. So what you're going to do is you're going to put a concave lens somewhere between the convex and the image. You will notice that I1 changes to I2. It's in a new position. So how do you figure out this new position? You follow these words. The image from the first lens is the object of the second lens. The image from the first lens is the object of the second lens. That's number 2. The image from the first lens is the object of the second lens. There, I've said it 3 times now, so that must be critical. Let's say for a moment, well, let's use the fact that I1 is 60 centimeters to the right. And I want, so this distance is 60. I want, trying to think of the number. They've got a good working set of numbers in the lab, so if I pick incorrectly, it's just going to be freaky. I'm going to pick that the concave lens is 15 centimeters to the right of the convex. So if this distance is 15 and that distance is 60, what is that distance here? 45. So this distance is 45. What you do is you treat I1 as O2. So O2 is equal to negative 45 centimeters. Remember when we were talking about mirrors, that you cannot have an object behind the mirror. Just doesn't make sense. You can have an object behind the lens. There's nothing preventing that. And so what we do is we treat the image from the first lens as the object for the second. And then we rerun the numbers. Let's say, for instance, that the focal length is negative 18 centimeters on that concave lens. So I2 is equal to 1 over F2 minus 1 over O2. Inverted. Plug in the numbers. 1 over negative 18 minus 1 over negative 45. Inverted. So the answer that we get please let the numbers work. Negative 30. Wow, that's an exact number. Impressive. Oh wait, whoa, back up. All right, here's the deal. What I'm gonna do is I'm gonna run this as normal. I don't like this distance. I have to recalculate a new number and propagate it. But what this image tells me, really what I needed is I needed to pull this concave lens further to the right. This image distance is negative 30. This means it is 30 centimeters to the left of the concave lens. So if this and this are separated by 15, then I2 is 30 centimeters to the left of the concave, which means it is also 15 centimeters to the left of the convex. So that's where it is. Now, once again, this plays a part in my whole philosophy of I don't really give a rip about the numbers. So fine, the image is to the left of everything. We know where this thing is. If the image is to the left of any lens, it is virtual. If the image is way over here, it is virtual. If it's between the lenses, it is virtual. If the image is real, it is to the right of both. For the image to be real, that sucker has to be to the right of both, which means that the final image distance, I2, must be positive. Now, this is one of the critical things about the whole thing. M2 is negative I2 over O2. The image distance is negative 30. O2 is negative 45. So this becomes negative 0.67. That's the magnification contribution of the second lens to the total magnification. The total magnification M, that M is M1 times M2. What you do to get the total magnification of the entire thing is you multiply the two magnifications together. The M1, negative 2. M2, negative 0.67. And so what we get is positive 1.34. So in summary, the image is virtual. Oh, so virtual. Now, what's going to happen in lab is that they've already figured out the numbers. In lab, you will get a real image. What you're going to do is they give you, there's an optics table, and you can move this plate back and forth, and you can find that image. It's not going to be like this. You will not get a virtual image on your compound lens lab. You're going to get a real image. That thing will just, boom, show up. So instead of what we did here, left of both lenses, 15 centimeters left of convex, you're going to get an image that's actually to the right of the concave. You will get an I2 that is greater than 0. Trust me, it's been done for decades. The magnification, when you did the problem in the problem set, I was very interested in understanding M1. And then you get to describe the image from the convex lens. And then I go, well, just give me the number for M2. And then I said, give me the magnification, the total magnification, and then describe the image. M2 means nothing to me. It should mean nothing to you except for contributing to the total magnification. M2 just is a number that plays a role. You don't look at it and go, well, it means this and this and this. No, it's a number that just passes on to the total magnification, which means that it is upright and enlarged. And that is the whole thing. Now, there are a lot of permutations to this. You can put all sorts of weird distances and focal lengths and object distances and image distances and all that. But the procedure is still the same. You calculate where this guy is from the first lens. You calculate the new object distance based on the distance between the lenses. You rerun the numbers again to find the final image. And then you discover both magnifications, multiply them together, and boom, there you go. There you go. So that's the compound lens. And that is one of the things that you'll be doing with this week and in the formal lab report this week. Any other questions? Yes. You want the homework moved to Thursday? I have heard. I shall now deliberate. Yes, you may have until Thursday. Thank you. I am a just dictator. Okay. Now start texting your friends to the 60% of the class that isn't here. Actually, you know what it may be? I take it back. Don't tell them. Everyone in the room, you may turn it in on Thursday. Let the people not here not figure. Oh, I'm gonna email them. Don't worry. Can we do it 5? Okay, 5. Doesn't matter. Noon, 5, 9. Huh?
5 on Thursday.
5 on Thursday.
What day was it due today? What time was it due today?
It was due at 6 today.
Okay.
All right, and I'll tell the 213s they're extended too. I'm in the Easter holiday. All right, that's it. Get out of here.